Welcome to our lecture Fundamental of Casting and Solidification. Today we are going to discuss core design in lecture 6. So, what is core? Core is a, a feature which is used to make hollow product in casting. Okay, like let us assume I want to make, as we have discussed in previous sections, 80 mm, this is 200 mm. So, what can we do? I want to make a hollow product. Okay. So, in mold, this is your drag and cope. How can we create a hollow product? So, I can place one additional feature of required size. Okay. A riser. Okay, and this is sand, kind of, it is made of sand which is made of similar to the mold, but strength can be different, but and it will be placed inside the cavity of the required size, that is core designing, the force calculation and all, and you can, after that solidification, you will just break this core. What will happen? There is no metal, only sand will be there, we can break easily and we can get hollow feature in this casting. So, core is used to make hollow product. So, core is made of green or dry sands. Okay, dry sand molding, green sand molding, as we have discussed in previous lectures. Similar method you use for core also. Green sand core are those which are obtained by the pattern itself during the molding. If your green sand mold is prepared during the molding preparation with the molding preparation. Dry sand core are made by a special core sand in a separate core box, baked and then placed in the mold before the pouring. So, you can see this kind of, we have just prepared this core and just place during the molding, or you have to prepare separately, or you can place in the molding and you can pour the casting and you can get a cavity after the breaking the core. So, you can see this want a course, this I want a hollow product like this, which is very complex, and you can see this is the core, and we have placed inside the before the casting, and this core is prepared separately, and what happens, we pour the molten metal, it will go all the places, but it will not go into sand because already sand is there, that core is there, you can't place liquid in that. So, what will happen after solidification, just you have to, what you have to do, you have to break this core and you will get this hollow product, and that will be very complex shape also, even that also you can get a hollow product, which is very difficult for other manufacturing processes like forging, welding, it is very difficult to get such product, but now additive manufacturing do. So, that is beauty of the additive manufacturing, and this core is made of either green sand or dry sand method. Characteristic of core and core sands. So, core must have sufficient hardness as well as strength in both dry and green state. Why you need two strength, we have discussed in previous lecture also. When we are pouring the molten metal, which is very high temperature, so what happens, green sand, there is moisture is there, the strength should be sustained before the pouring also, because it not loose, so loose that it is going to break and you can't get a hollow product. So, they not nothing to so you need some green strength, but when you are there is sufficient green strength, you are sustaining the system. But what is happening, you are pouring the molten metal like aluminum 700 degrees Celsius, at that temperature moisture or water contained in the sand mold or core evaporates, burns, and what happens, that go into, if that mold has no strength at that temperature, what will happen, that is called dry state, and when moisture is not there, what will happen, if no sufficient strength, it can collapse. During the collapse, again we will not get a hollow feature what we want. So, for the purpose we need hardness as well as strength in both state. Okay. Without this property, core will not able to support its own weight and withstand the force of molten metal. We will understand this forces, okay, in upcoming slides. Core must be permeable to allow the core gases to escape easily. See, as moisture is going to evaporate or boil, or if too much temperature is very high, so evaporation will happen and it will try to escape the gases. If you are not done proper permeability of cores, what will happen? It is going to create defect like blowholes, spring hole and all, and the internal feature of the casting. So, we have to give a permeable sand core, so that gases can escape from the core and it can go out from the mold. Core should be able to withstand a high temperature of molten metal that we have discussed. The produce a minimum amount of gas so that very high permeability is not needed and greater strength is imparted to the core. Core should be collapsible. All mold, all sand should be collapsible when after casting. When we have completed the casting, we have to break that mold and it should be easy, too much easy. If you are not able to break, you will not able to achieve, you will not get your product from the casting. So, it is no meaning. So, what you have to do, you have property should be also that after the casting, it should be easily breakable, okay, easily collapsible, okay. Essentially, core sand must have a very similar property to that of the molding sand, except when the cores are thin, they need to have a high strength to overcome buoyancy force, high thermal gradients and able to crumble for easy removal of sands. So, you can see some examples. I want a hollow feature. So, this is the core and this is our product, and product with some allowances. We have product means some allowances already there, like shrinkage allowance, machining allowance, draft allowance. You can see draft allowance is already given here. You can see, okay. You will see draft allowance is already given to the this pattern design, and pattern this you can see extra features. This I don't need in product. I don't need. I need only this, and this, which is hollow. Okay, like this. But in pattern, what you have to make core also. For the core provision, this is the core prints we will discuss later. This is the pattern where extra feature has been added for the core, and in that place we are placing a core, and after the casting, when molten metal is poured here, pouring after solidification, we break this and we break this sand also, core also, and we will get hollow product. What will the product feature? Okay, this is hollow product we will get in casting. So, types of cores, 3, I will not go too much in detail, I will go briefly. So, 3 will be 3 obviously vertical and horizontal core. So, we can see here this is vertical core, this is horizontal core, okay, by the position. There is cover core, there is called cover core, which is going to cover whole mold from the, there is 2 core prints, this is called core prints. Extra, this is called core prints to support the core. We will understand this thing, just understand the terminology first. So, this is core prints to support our hold or positioning our core in the mold. Okay. This is an additional feature, additional area. So, cover core, which there is a both side core prints. Cover core means both side core prints. Whereas balance cores, balance you have to balance in such a way, but there is no chance to make core print in both side. You are not able to position, you are means your core prints are not on both side, means there is no covering, only one side is able to hold your core. So, that is why this is called balanced core. Okay. And how we decide it should be balanced, or obviously we need, and you have to calculate. See, you can see that length, it is very high length, L is and this L is, isn't it? So, you have to balance this, and that calculation we will see in next slides. Similarly, drop core. Okay, drop core, a hole on recess to be obtained by the casting either below or above the parting line. In this case, we are getting hole near the parting line. This is the parting line, this is the parting line. Okay, we are want to hole around the parting line, but if you don't want hole near the parting line, like you can see, I want hole in this position. It is not near the parting plane. The parting line is this. Then what you have to do? You have to add a drop core method. Okay, core prints. As we have discussed, this additional features is called core prints. For supporting the cores in the mold cavity, an impression in the form of recess is made to the mold with the help of projection suitably placed of the pattern. This extra projection is known as a core print. The core print must be adequate size and shape. So, take care of the weight of core before pouring and the upward metallostatic pressure of the molten metal after pouring. The core prints should also ensure that core is not shifted during the entry of the molten metal into the cavity. It should be stable, it should sustain the temperature, it should be permeable, and it should be green strength also, as we have discussed. So, core prints we have seen, these are the core print. In horizontal, this is vertical core, you can see these additional features are to support and withstand in the cavity. Okay, this additional features is called core prints. Okay, now why you need core print first? Okay, so before going to that, if molten, if you are liquid, if there is a liquid like ocean or anything, and something is submerged. Okay, something is somebody. I am just taking a cuboid. Okay, is submerged. Okay, okay, something is submerged. Some object, area A, cross section area from the top is A, height is x. Okay, this depth is h. So, there will pressure, hydrostatic pressure will work. Okay, and that pressure value will be rho g h. Rho is the density of liquid. Okay, density of liquid, g is the gravity acceleration. Okay, 9.8 meter per second square. H is the depth of the water. Now, similarly, in this direction also pressure will act. Similarly, this direction hydrostatic pressure will act, but what is happening in this direction, they are opposing to each other. So, it will cancel out. Similarly, from the front and back, they will cancel out. We will not discuss too much in that, but in what will happen with the bottom? Again, hydrostatic pressure will work, and what is the value? Rho g h plus x. What is the depth? H plus x, the object depth. So, here what is working? What is pressure? Rho g h plus x. Again, rho is the density of liquid. So, difference will be, what is the pressure difference on this object? From the top rho g h, from the bottom rho g h plus x. So, rho g h plus x minus rho g h. So, what will happen? Rho g x. The pressure difference will be rho g x. Now, area, force. Force on body will be pressure difference rho g x into area on acting area. Which area it is acting? On the this area, cross section area we are taken A from the top view. So, rho g x into A. So, rho g x A. And what is x into A? A is the cross section from the top and H is the X is the height of the body. So, what will it will be volume, okay, and that is known as a buoyant force, buoyancy. If any object is submerged into the liquid, what will I experience? I experience a buoyancy force. The value will be rho GV. V is the rho is the liquid density, that is kg per meter cube. V is the volume of submerged object, okay, and G is 9.8 meter per second square, okay. So, any object in the submerged in liquid, there is going to be a, and what will direction? Direction will be, this is rho g h and rho g h plus x. So, upward is higher and downward is lower. So, overall effect will be upward direction, okay. It is acting upward direction. So, buoyant force is acting upward direction. The buoyant force will be rho metal. Obviously, what is happening here? In core, you are placing your core in a molten metal, okay. So, what is happening? Rho g h, let us assume, what will happen? Let us assume this is a x, rho g h plus x, isn't it? So, what is happening? You are applying a force rho g v. You are applying a force, buoyant force is rho g v. Rho is the density of molten metal. Rho will be rho metal. G, v is the volume of core. Where it is acting? On the core, isn't it? That much force is acting. So, that is why if what is the direction? It is upward direction. Now, something even not doing anything, just pouring, there is a upward force is acting on the core. Now, if something is going up, applying on the core, you have to, it can break, isn't it? Some additional force is applying on something, and if you are not able to sustain, it can break. So, what happened? You have to hold somewhere, either both side, single side, or somewhere you have to hold such a way that it can sustain into the mold cavity in molten metal presence, okay. That is why you have to need core prints, okay. Hope you are able to understand this phenomena. Now, someone is asking what is the net force on core. So, we have understand the buoyant force. What is that? Rho metal buoyant force equal to, I will write buoyant force, then you will understand. Force equal to rho metal into G into volume of core, volume of core, okay. Now, let us assume this is there and force is upward, rho m g v, but core has some weight. It is upward direction, in upward direction, but core has some weight. Weight of core will be rho sand into g into v, volume of same, okay. So, net force will be net force, upward force, buoyant force minus downward and weight of core. So, rho metal G into V minus rho sand G into V. So, what is the common? Rho m minus rho sand into G into V, and which is acting upward and downward depending on the value. But in general, since rho density, rho of rho metal is greater than rho sand, 1.65, this is 7.8 for steel. For the aluminum 2.7, it's always higher. So what is the direction? It will always look upward. It will always upward. So net upward force is calculated the difference of weight of liquid metal, that is core material, of the same volume to be exposed core. So we are able to understand this. Okay. Gram per cc I am light, then gram per cc, gram per cc. Okay. Around that the value is, so rho m minus rho core is always positive because of density difference is higher. Okay. So its direction is always upward direction. So force on any force, how much force is acting? Rho metal minus rho sand core, whatever density you take in mold material, into G into volume of core. That much force is acting upward direction. Now we will go for a one time of horizontal core, one time vertical core calculation, then you will understand. So this has given D, the diameter of core is D, and how you will get D? Let's assume in previous questions we have in lectures we have taken 80 mm hole. So what is the core diameter? Diameter will not straightforward as a 80. You have to first add your design your pattern. Pattern you have to shrinkage allowance, then machining allowance, then draft allowance. Based on that you will calculate your D. It will not 80, it will be lower than 80. Okay. So P equal to the force on core will be P metal minus P core into G into V. Very simple. Okay. Its force is this, mass rho sand or rho core, I can write rho core, core means sand, into G into V. This is downward, and upward is buoyant force is rho m G into V. This is upward force, upward buoyant force. So difference will be rho metal minus rho core into G will be there. What is the volume? Volume will be pi by 4 d square into h, the volume of the material which is exposed into liquid. Okay. Now, but if you are going for the vertical core, here you have something you have to be very careful. So what is that? Rho m G into V core in liquid, P equal to minus V core into G into V core. Why? In in buoyant force, how much liquid is exposed? This much volume, but this additional has no weight calculation. So in this case V core will take this and V will taken by this in for the buoyant force. So what is the value? Rho m, obviously G will taken common, pi by 4 the area, first area, pi by 4 d1 square, pi by 4 this area, pi by 4 d1 square into h, this volume, pi by 4 this area volume, pi by 4 d square into h1, pi by 4 d square h2 divided by 4, this thing we can, which is in liquid. But here what will happen, the volume will be addition of this plus this plus this plus this also. What is that? Pi by 4 d square h4, pi by 4 d square h3 also. So what will be the total summation? Pi d square into h plus d square h1 plus h2 plus h3 plus h4 and divided by 4 into multiply by g. This is the basic concept. You can solve the numerical problems for the vertical core. You have understand the forces on core, and now you have to design your core print also. You know the dimension of the core by the pattern design and okay, shrinkage allowance. Then after you have to calculate all the allowances, you have to calculate your core dimensions. Now the forces you know. Now what you have to design? The core prints this area. This the how much length? H3 and H4. H3 and H4 needed or not, that depends on the balance core, vertical core or horizontal core on the design. But H3 and H4, if someone will be there, either H3 or H4, whatever will be there, but something will be there, either H3 or H4 or both. If in both or single, anything happens, you have to calculate the length. H should be there, which length, how much length to hold that support. So, what obviously, if you know the P, you know the P is the unbalanced or upward force, you know the upward force you know. So, it should be managed, P should be managed, otherwise what will happen? If some metallostatic pressure is acting or hydrostatic pressure is acting, it will break the mold. To avoid that, what will happen? To avoid that, we have to hold that core print by length, by some dimension. Okay. So, there are two empirical relations. There are two empirical relations are there. So, first empirical relations, and the core print support by a load of 3.5 Newton per cm square. So, buoyant force, so not buoyant, net buoyant force P should be less than and equal to 350 A. And what is A? A is core print area. So, from the, I can show from the top, this L, L and D. So, area will be 2LD, 2L, sorry, L, LD. Let us assume only one and hanging kind of core is there, LD. Okay. So, A will be LD. Projection area you have to take L into D. P less than 350 A means 350 into L into D. I am taking this case. If you are taking this case, so what will happen? P less than 350 into 2L into D. Okay. Based on that, you have to calculate your D. You already know, you can calculate your L, and then you can design. If above is not satisfied, then let us assume it is not satisfying. You are doing something, you are calculating, you are designing, but mold is not too much big. Okay, you are not able to get L sufficient. Then, if you are not able to satisfy, then it will be necessary to provide additional support to way of chaplet to describe the, which is described later, we will discuss just after this. From the core print area, necessary core print size can be calculated. And second relation is called area of the core print is greater than K P by sigma, K P by sigma. Sigma is already given by the mechanical properties, which is 350, you can calculate. K is value is taken. So, K small k is 0.5 to 0.7, it depend on the practice. These are empirical relations. Okay. Same A you know, LD, 2LD depends on the projection area at the parting line, you can calculate this. Okay. Now, core chaplets. Now, if you just take your core print is this hanging in that. So, your P is so too much high, P is very high because you are not able to hold too much. So, what can you do? You can place some support from the top, so that it balance your extra P. P is so high, so that you are placing some additional tool or additional support from the top, that is called chaplet. Okay. Chaplets are metallic kind of thing, which composition should be same as the molten metal, because it is going to merge with the molten metal only, it is going to dissolve. Okay. Just what you have to do, it is going to support the hanging core or unsupported core. So, chaplets are often required to place between mold wall or base and core in border to avoid deflection of core and achieve the exact section thickness of the casting. Unsupported load, obviously P minus 350A, which is P is the upward force and 350A is that core print holding load force. If you are subtract that, you will say you can send unsupported load, that you have to manage by the chaplet. As far as possible, chaplet should be the same composition as the cast metal, so that homogeneous structure is obtained, no internal flaws are developed. No internal flaws can be developed, no inhomogeneity can develop. Chaplets are a small piece of the metal having a height equal to the space between the core and mold wall. Okay. Based on that, you can design your chaplet and place your number of chaplets. Let's assume your P is 1000 and A is 1 and unsupported area load is 650 okay Newton, okay, something like that, 650 Newton, and one chaplet is able to take 150 Newton. Okay, so how many one chaplet take 130 Newton, so 5 chaplet, at least 5 chaplet needed. Okay, at least 5 chaplet needed to support your unsupport load. Okay, hope you understand the designing of pattern, core and all in detail. Thank you.